Hello everyone, welcome to all in this lecture. So in this lecture, I'm going to design a strap footing. So strap footing we can design in the two cases. So the first case we have when suppose if one straight column is touching the property line. This is the property line. One column is here, Q1, Q2, and here the total resultant load are coming. So distance of total resultant load from the exterior face of exterior column is X dash. So suppose this X dash is less than L by 3. So in this case, we can go for design of strap footing. Second case also, if we will discuss, if we'll see second case. So when the two columns, distance between two columns are large, okay. So in this case, what we will see, if we will design the combined footing, that will be narrow and very long, and that can be uneconomical also. To avoid such things, what we will do, we will design the strap footing. Okay, so in the strap footing, we will first design the isolated footing for both the columns. Or we can set a split footing, and then we will design a rigid beam. So that will we have a connecting link between the two footings. So this is called the strap. This footing is called strap footing. Okay. So this strap footing does not hold any soil reaction, does not take any soil reaction. Okay. So what is work of this strap footing? So this strap footing transfer bending moment from exterior footing to the interior footing. It transfer the bending moment from the exterior footing to interior footing. So let's discuss the design of strap footing. So in this figure, you can see most of the notation we know already. Q1, Q2, X2, X dash, X bar. This is the strap. So here you can see there are R1 and R2. What is this? This is the reaction. Or we can say this is the resultant reaction below the isolated footing or a split footing. And that is below the exterior column. Okay, and R2 is the total reaction below the interior column. A distance between both R1 and R2 is S. Distance between both loads is X2. Here the E is the eccentricity. What is this eccentricity? You can see in this second case, line of action of load are on the same line with the resultant. So there is no eccentricity in this case. But you will see in the first case, the line of action of load Q1 is not lying on the line of with the resultant. Okay, so this is called the E, distance between line of action of load Q1 to the R1. Okay. Here B1 and B2 is the cross section of column 1 or exterior column, B2 into B2 cross section of this. In this case, you will see this is the footing provided for the interior column, that is square. So both length and width is B2. In the first case, we will see due to eccentricity, there is we have to provide the rectangular, and also we cannot go for the projection in the left direction beyond the property line. Okay, so here the length L1 is length and B1 is the width of this rectangular footing, which is provided for the exterior column. And then we have then there is a design of there is provided a strap footing, strap beam we can say, or we can say simply a strap. So this is beam design. This is connecting to first footing to the second footing, so that bending moment will transfer from the exterior footing to the interior footing. So there are some standard procedure and that we will follow to design the strap footing. So when you follow the steps, it is very easy to understand. what we have to know and what we have to calculate. Okay, so you will see your solution is coming in a step by step, so that it is very easy to understand. Okay, so the first what we will do, we will calculate or assume eccentricity. Okay, so either when you are going to design in the whatever the problem is given, so maybe E will be given in the question, or if E is not given in the question, so you have to take some, you have to assume some value, right? So according to your assumption, you can proceed further design. Okay, further design procedure. So we cannot, we should not take the E value very larger, so that it is a uneconomical for the uneconomical, and we cannot take E value very less, so that it will be it cannot balance the soil level pressure. So we have to take the E value in between. Okay, so after assumption of E, we can calculate length. So how we can write this equation? See, what is E? E is the distance between here to here in this figure. And what is this distance? This distance is B1 by 2. You can see center to exterior face of exterior column. So this is B by 2. Or also we can write 0.5 B1, right? So this total length, this is E plus 0.5 B1. And this is the center of this footing. So how it will come center? When this is the half length of footing, right? So this will be equal to half. So the center will be lie here. So center of gravity will be lie here. So from this here, we can write L1 is equal to 2 into E plus 0.5 B1. So now you have the idea how it came. Now, once we have the E value, we have the L1, so we can calculate, and we have the Q1, Q2, X2. So we can calculate the reaction, R1 and R2. R1 is the reaction, or we can say total reaction uh, below the first footing. Okay, and R2 is the whatever the total reaction coming for the second footing, and footing for this interior column which I have provided. So we can calculate R1. So how we can calculate R1 and R2? So I'm going to explain. See, suppose this point, suppose this is the P, for example. Okay, so I am taking moment along the P, and I'm taking the sign convention that clockwise moment will be positive. Okay, so see, Q1 is load coming on this point P. So here we can write Q1 into 0. Okay, plus Q2 into X2. Can think distance between P to this here is X2 minus R2. We can write R2. So what will be, we can get, we can write here R2. What is the distance from the P? That is S plus E minus R1 into E, right? By simplifying, we can write Q2 into X2 minus R2 into S minus, we can write E into R1 plus R2. So this is the equation first. Second equation, we can take this summation of all the forces in y direction is 0. Okay, to get the equilibrium of this footing. So what will happen? Minus Q, per direction I have taken positive, so minus Q1 plus R1 minus Q2 plus R2 equal to 0. So we can write R1 plus R2 equal to Q1 plus Q2. So here is two unknown R1 and R2. So we can calculate. So we have the two relation. We have the two unknown R1 and R2, and we have the two equation, first and second. So by solving these two equation, we can get R1 and R2. And there is other method also I can discuss. Not other method, if we will take the moment at a different location, we will get directly R1 value. So I'm showing that also. This is also good. You can solve by this also, but that will be easy if you will follow this. What I'm going to show. See, select this point is, suppose this point is B point, for example. So take the moment, bending moment at a B point. Summation of all the bending moment clockwise direction will be 0. So now what will happen? This point, okay, so Q2 into 0. And also we will see, suppose we can write minus R2 into 0. So this will be nullify. Then we can write minus Q1 into what is the distance? B2 P or Q1. So that is X2 plus that is R1 will be called the anti-clockwise moment at a point B. So we can write R1 into S. Okay, so we can write from here that Q1 X2 is equal to R1 into S. So from here we can write R1 is equal to, sorry, R1 is equal to Q into R1 is equal to Q1 X2 by S. So same thing I have written here. By taking the 7 in the summation in the upward direction, this we will apply this. So I'm taking the upward direction, upward force, say that is positive. So from there we will get R2 is equal to Q1 plus Q2 minus R1. Because you will see on this footing, there are 4 forces Q1, Q2, R1, R2. Okay, so you can get these two equation. By using these two equation, we can calculate R1 and R2. Now, once we have the R1 and R2, then we can calculate A1 and A2, where A1 is the required area for the footing, for the first footing, and A2 is the required area for the second footing, second isolated footing, we can say, where Qn is the soil allowable pressure, and R1, R2 is their reaction. Okay, so by using this relation, we can calculate a required area for the first footing, that is rectangular in shape, for the second footing, that is square in shape. So now once we have the area, then we can calculate what are the required width, what are the width required. So B1 we can calculate, we have the A1 and L1. Okay, and B2 we can calculate because this second footing, that is a square, so taking the root under of this A2, we can get the B2. So here the B1 and B2 are the required width for the rectangular footing and for the square footing. Once we have the B1 and B2, so now we can provide some extra to be the safe side. Once we have provided the this extra width, then we can calculate provided area. So by knowing the provided area, we can calculate the actual pressure in both the cases, actual pressure for the first isolated footing, actual pressure for the second isolated footing. So I've given the name, that is Q01 for the actual pressure for the first footing, that is rectangular, Q02, that is actual pressure for the second footing, that is a square in shape. So once we have the actual pressure, then we can calculate intensity. Once we have the intensity, then we can draw the shear force diagram and bending moment diagram along the length of the footing. So at a geotechnical point of view, we have to calculate, we have to solve this design problem up to this level. We have to draw the shear force diagram and bending moment diagram. Once the bending moment diagram and shear force diagram we have drawn, so we can see whether a bending moment is maximum, whether the shear force is maximum, whether the bending moment is minimum, at what section, what value of the bending moment in shear force. So we can calculate. And after the knowing this maximum bending moment, we can design the strap. We can design the a rigid beam. Okay. So now I'm going to solve one, discuss one design of a strap footing. So design of a strap footing for the two columns shown in the figure. The allowable soil pressure 100, QNA is given 100 kilonewton per meter square. Okay. Okay, E is given. Take the eccentricity of the footing, that is 1 meter. So E is given 1 meter. Q1 is given 600 kilonewton, Q2 1000 kilonewton, X2 is given 6 meter. Here the AC is given 5 meter, E is given 1 meter. Cross section is given B1 into B1, 0.4 into 0.4. B2 is given also, B2 into B2, that is given 0.4 into 0.4. This is the strap footing. This is the two isolated footing, we can say. Okay, so now we will follow the procedure to calculate all these values. So first we will calculate E, or we will assume E. So in the question it is given 1 meter. Now we can calculate L1, that is length for the first footing. So we have this formula. So we get 2.4 meter. Once we have the L1, we can calculate R1 and R2 reaction. So all this formula which I'm using here, so I have discussed how it came. So R1 we got 720 kilonewton, R2 we got 880 kilonewton, 880 kilonewton. So once we have the R1 and R2, we can go the required area. So required area A1 we have 7.2 meter, we got, and A2 we get 8.8 meter square. These are the required area for both the footing, both the isolated footing. Once we have the area, we can calculate their width. So required width, that is B1, we get 3 meter. Required width B2, we get taking the root under of A2 for the second footing, which is below the interior column, that is in a square in shape. So that is we got 2.96. So I'm assuming we are providing 3 meter to be safe side. Okay. So once we have the V1, B2, so we can calculate what are the actual pressure in both the cases. For the first footing, we are getting actual pressure, that is R1 divided by A01. Okay, so see, we get 100 kilonewton per meter square. So this is the actual pressure is same, equal to the allowable soil pressure. So why it is same? It is same because we have provided same area that we get for the first footing. For the second footing, for second isolated footing, Q0, we get R2, that is soil reaction divided by A not 2. So we get 97.8 kilonewton per meter square. 97.8 kilonewton per meter square. So these are the two actual pressure. So here, so we can then we can draw shear force diagram and bending moment diagram. So here we get actual pressure 100, and in this case we got actual pressure. I've given the name also, 97.6, 97.8. That is less than 100. That is equal to, what is this 100? This is QNA. In this case, this is equal to QNA. Okay, so now we can calculate the pressure intensity. Now we can calculate pressure intensity. So what is this pressure intensity? See, here we are getting Q naught is 100. So this is the pressure kilonewton per meter square. So we have to take the intensity. So what will be the intensity? So we are calculating the UDL. So what will be the Q naught into P1? Q naught, what is Q naught? Q naught is 100. What is B1? 3. So it will come 3. What is the B1 we are getting? Yeah, 3 meter. So it will become 3 kilonewton per meter. So this is the intensity we are getting here. Now here Q naught is 97.8. So we will calculate intensity at the base of this footing. Direction will be in upward direction. So we can write Q naught into B2 means 97.8 into 3. So we will get some value, and that is we can calculate 98 293.4 kilonewton per meter. Okay, so now once we have the intensity name, then we can calculate, or we can draw the shear force diagram and bending moment diagram along the length of the footing. So first, before drawing the shear force diagram, first draw a line diagram so that we can understand it better. So I have same thing I have mentioned here. You can see that this is the 300 kN per meter, that is the intensity, and 293.4 kN per meter, that is the intensity below the second footing. Okay, now so see, this is the line diagram. You can see, so distance between both the column is x2, that is 6 meter. Here you can see 0.2 meter, here 1.5 meter, because this total is 3 meter. This is the intensity Q naught 2 into this one, the I think this is the B2. Here we can see this 300, this is the Q naught 1 into B1. Okay, so this is the intensity kilonewton per meter. Here it is the here is the L1 length 2.4 meter. Here is the B2, because this is the square in shape, and this is the rectangular in shape. Okay, now we can draw the shear force diagram. So by drawing the shear force diagram, you can see, so how we can draw the shear force diagram. So I'm taking some sign convention. So I'm taking, this is the sign convention. So if you will calculate from the right side, so the forces in upward direction, that will be positive. Forces in downward direction, that will be negative. So shear force at a point, it means either from the left side and right side, total resultant force in this direction perpendicular to this plane. Okay, so we can calculate now. Okay, so let's look at some point, that is this point is A, this point is B. Somewhere here you can see, let it be A, B, and this point is here. You can see here A, B, C. So each endpoint, B just below this concentrated load, C is the end of this ideal load. Here this point is D. Here point just below the concentrated load is E. At end point there is a F. So A, B, C, D, A. Okay, now we can locate A. So we can calculate the shear force at a point A, that will be 0. So now we can calculate the shear force at a point B, just left side of this load. Okay, so we can calculate shear force at B, just left side of this B. So we'll get the pressure, that is we are going to find for this value 0.4. This intensity is 300 kilonewton per meter. Usually in upper direction, so that will be positive 300 into 0.2. So we can write 60 kilonewton. and that will be in the linear because here the UDL, uniformly distributed load are here. This is UDL. This is also UDL. Okay, so here we will see this is 60 kilonewton. Now we will find some sudden change at this point B. So what will happen if you want to calculate the shear force at B, just right side of this B, so you will get plus 300 into 0.2 minus, this is in downward direction, so downward direction is negative, so you can write minus 600. So you will get 60 minus 600, that is minus 640 kilonewton. So you will find sudden change at this point, and that is minus 540 kilonewton. Okay, now we will calculate the shear force at point C. This is A, this is B, it is positive. So we calculate the shear force at a point C. So let me erase all these things. So we will find the value at a point B. So we can calculate here. So first I am showing what is the this loading condition. So shear force at point C. So we will find like this. So this is the loading pattern. This is point A. Here the load is coming 600. Here the point B. This is the point C. So we are going to calculate shear force at this point. Okay. So we can calculate positive 300 into what is this distance A to C, 2.4 minus 600. So what you will get? 720 minus 600, that is plus 120 kilo Newton. So you can find here we get plus 120, this value I'm getting here. So here is 120 kilonewton plus. This will be linear. Okay, this is linear, and in the picture is like it's like this is a non-linear type, but this is linear. Okay. Okay. So here this value is 120. So it will go up to here. Wait. Okay. At a point C, C is here. This is this is 120, right? Okay, this is 460. Okay, now you will see in the there is no force in between C to D, so shear force will be constant. So at D point also we will find shear force 120 kilonewton, that is positive. Now we can calculate shear force at a point, this point E. So we can calculate shear force at a point A. Now we are coming to, we can calculate from the left side. So that will be plus 300 into 2.4 minus 600. Now again, it's here. Okay. So this is also upward UDL load. So we can calculate plus 293.4 into what is the distance? This is total 3 meter. So this will be 1.5 meter. So we can write 1.5 meter. So we can get a calculator. So I'm writing directly. So we can get at this point 560. So here it's coming 560 kilonewton. That is positive. Now at the 560 you will get the sudden change. This is concentrated load in the downward direction. So downward direction when you are calculating from the left side, so downward direction will be negative. So we'll deduct 1000. So it will be here something 440. That is minus kilonewton. This is negative. Then you will come to finally it will reach here 0. So this is the shear force diagram. Okay, so you will find you will see in the this bending moment diagram at a point B, and at this point you will find there is a shear bending moment force is maximum or minimum, because the shear force is here is 0. So also we can find this point, so at where it will be shear force will be 0, so that we can calculate by taking the x-axis. So that I'm showing here. I'm taking one x-axis at this point, and this x-axis is at a distance x from left side. So we can write shear force at a x-axis. So that would be 300 into x minus 600. This is plus, okay? So we can calculate the x would be by taking the 0, x would be a 2 meter. So we can say at a from here to 2 meter, shear force will be 0. So this point I can give a name, A, B, C, D, E, F. This point is G. Okay, this point is G. So at a 2 meter from the left, there is a shear force is 0. Now we can calculate the bending moment diagram. So for the bending moment diagram, I'm taking the sign convention. So this is the sign convention. If we are calculating from the left side, so anti-clockwise moment will be positive and clockwise moment will be negative. Okay, so let's calculate. Again, I'm locating the point A, B, C, D, E, F, and here the point where the shear force was 0, that is G. So distance between G to end, this is 2 meter. Okay. Now, so bending moment at a point A will be 0. So we can calculate the bending moment at a point B. So you can see this is the upward forces acting here. So the moment will count anti-clockwise, sorry, clockwise. So that will be negative. So we can write minus 300 into 0.2 into 0.2 divided by 2. Right. So it will come here. So we can calculate this value. So this value you can get. I've calculated here. So I'm writing directly. So you can get this value minus 6 kilonewton meter. And this will be not a linear. So we can check also the curvature. So we can write minus 6 kilonewton meter. Now we can calculate the bending moment at bending moment at this point G. We can calculate the bending moment at a point G, so that we can get this value. No, we are going to calculate the. So we can write. We can write at a point G. So we can write minus 300. What is the distance? G point from the left side, that is 2 meters. So 2 into 2 divided by 2. This is the force. This is the center of this force to the section where I'm calculating, right? And then one is a concentrated load, so that will be a positive. So 600 into 2 minus 0.2. 2 minus 0.2. So you can calculate. So I have already calculated, so I'm writing directly. So that is 480 kilonewton plus. Now we can calculate bending moment at this point, at a point C. So that will be the minus 300 into 2 by, no, not 2, sorry. 300 into 2, 300 into, what is the distance? 2.4. 2.4 into 2.4 divided by 2 plus 600 into 2.4 minus 0.2. Okay, so that we can get, so I've calculated, so I'm writing that we get 456 plus 456 point, 456 kilonewton meter, right? So at the point, this point G, we get 480 kilonewton meter. At a point C, we get this value 456 kilonewton meter. Okay, now we can calculate the bending moment at other points. Okay, so we can calculate the bending moment. So see, here it minus or here it is a positive. So somewhere you will see that bending moment is 0. So we can find where the bending moment is 0. Here will be the maximum at a point G. This is the point G and this is the point C. Okay. Now we will find where it bending moment is 0. So I'm taking a section XX, that is distance X from the left. So we can calculate bending moment at X, that is minus 300 into X by 2. X into X by 2 plus this 600 minus this X, it's minus 0.2. So by equating this value 0, we can get the value of X that we are getting. So we can get by putting this bending moment is equal to 0, we get the X value, and then X value is 0.211. So it will somewhere else here. X 0.211 meter. So here the bending moment will be 0. So now we can calculate the bending moment at D. So bending moment 0 at D, we can calculate. So that will be minus 300 into 2.4, that is force. Now we can calculate the center of this force to the section. So that is at a point D. So what will be the D? So we can write 6 minus 1.5. What is this total length? Leave with the total length. 6 minus 1.5. So we reached here to here. Okay, now we will add 0.2 minus 1.2, right? Then positive 600 into this no, we can solve like this also. Okay, we can write like this. See, this is the total reaction. Okay, so minus 300 into minus 300 into 2.4 into we can write this 5 minus 1.5 plus 600 into plus, because this is this value is distance is to here. Okay, and then plus E, that is 1. So that you will get, I have calculated, so I'm writing directly 180 kilonewton meter positive. Now we can calculate bending moment at this point at E. So that will be minus 300 into 2.4 into 5 plus 600 into 6. Then again minus 293.4 into 1.5 into this 1.5 divided by 2. So we'll get this value, that is minus 330 kilonewton meter. So now we can draw the bending moment diagram. Here we are getting 180 kilonewton meter, that is positive. Here is a negative. By taking the bending moment is equal to 0, by taking the section, then you can calculate this value, what will the distance from the here. Okay, so this is the bending moment diagram that you can show. At the point G there is bending moment diagram positive 480, at a point C there is a 456, at a point B minus 6, at a point E that is minus 330 kilonewton meter. Okay, so once we have drawn this bending moment diagram and shear force diagram, then our work is over from the geotechnical point of view. If you are going to calculate the concrete design and we are going to design reinforcement, we need to calculate the reinforcement value, area of the reinforcement diameter, and then we have to calculate the effective to all those things. But at geotechnical point of view, we have to calculate only shear force diagram and bending moment diagram. These are the some difference that I've taken to make this lecture. And thank you. In the next lecture, I will discuss the design of mat foundation. If you have any doubts, then you can ask. And if you are by calculating you are getting some different value, then you can leave the comment in the comment section. Okay, thank you.